Hello, my name is Richard Turner and I'm going to give a talk today on the finite element modelling that we can do as part of the AMCASH project. I'm a research fellow at the University of Birmingham. Okay, so why would we want to use the finite element method to model metal forming or another manufacturing operation? Well, potentially there's expensive costs of the raw material that might be used up in a trial and error approach if we're trying to optimise some process parameters, so modelling can alleviate that. A trial and error approach might entail experimental work that ties up a production machine at your company, and maybe you've got a limited number of machines and you can't afford for one to be tied up for a long time. So again, modelling can alleviate that. There might be an environmental impact. There might be targets that you need to hit as a company, and we can help to reduce the wasted raw material and reduce the carbon emissions from running your machinery. And further, modelling can give a detailed understanding about the process, so we can understand more about what's happening inside the metallic billet that's being formed that would be achievable from standardised testing alone. So hard to measure fields such as the evolving stress, strain and strain rate within a structural metal billet can be visualised with finite element modelling. So the university has got licenses for a number of software. We've got a specialist metal forming software, we've got a specialist welding code, we've got a more general purpose finite element software that we can use. We've got experience in FE simulation of various metal forming operations, including drop forgings, press forging, cogging, upset forging, shape rolling, friction welding, and laser and electron beam welding. We've got experience in different types of material, so typically metals. We've got experience in steels, in titanium alloys, and in nickel alloys. So the first FE model that I'm going to talk to you about today is a press forging. So we start off with a very simple shaped billet, a cylindrical billet. We start off with tooling that has a recess within the tooling of the relevant shape that's being forged, and we apply a force, and we see that our simple cylindrical billet is deformed into the relevant shape within that recess within the tooling. So in order to perform accurate models, we would need accurate representations of the geometry of the billet and of the tooling. So we would need these as computational files that we could use. We apply a mesh to our workpiece, our billet, so you can see on that billet now there are a number of triangular elements over the surface, and these are three-dimensional tetrahedral elements that make up the billet as it's being deformed. And we can see the temperature profile on that video as it plays through, and we can see particular hotspots that are being formed during the press forging operation. So the second finite element model I'd like to talk to you about is a shape rolling model. So again, we start off with a very simple shaped workpiece. This is a rolling model, so we're applying different rollers back and forth over our workpiece. We start off with top and bottom rollers, and then we add some side rollers in. And as we pass our workpiece back and forth through these moving rollers, we can see the emerging shape of an I-beam as it's being constructed through this mechanical process. Again, we need accurate representation of our initial billet and our tooling, our rollers in this case, to make our model as accurate as possible. And again, we can see a temperature distribution over that workpiece, so we can see any hot spots or cool spots that are forming as a result of the process. So the last process model that I'd like to talk to you about is rotary friction welding. So in this process we have two components, two axisymmetric components. The first remains stationary, the second rotates about its axis of symmetry. We apply a load across the two, and the frictional heating at the interface causes the components to bond. We can see the video playing through in the top left corner of the process, and in the top right we can see a process model of an inertial weld. So again, we can see that our process model can begin to predict things like the temperatures, the stress, the strain, distortions, and the flash formation in this process. So we can see that we can get quite an accurate representation of the real process using our modelling technology. So that brings the presentation to a conclusion. If you've got any interest in using the AMCASH project to support regional SMEs in the West Midlands, then you can contact myself, or you can contact the AMCASH team with the contact details on screen. Thank you very much.